All right. Hello. Welcome back. Thanks for coming by. And we'll continue on our journey and looking at weak memory models. So yesterday, I was showing you this x86 model that I call x86 TSO. And first off, before I get off to exciting, even weaker memory models, I thought what I'll show you is a different style of looking at memory models, a somewhat more abstract model. And these are what's called axiomatic or declarative models in the world of memory models. And there's two reasons for bringing it up. Well, many reasons for bringing it up. They are obviously interesting. They have good properties, which I'll show you about. It also links quite nicely with what Glenn was talking about in the morning. And finally, yet another reason for talking about it is I was asked about some aspects that become easier with axiomatic models yesterday. So I'll hope to give you a quick flavor of all of that. So what's axiomatic models then? So axiomatic models, they are a much more declarative style. They're phrased in a much more declarative style than the kinds of modeling we were doing yesterday when, you remember, we were talking about abstract machines. So the idea of axiomatic memory models is to consider the set of executions of a program, or I should say candidate executions. And I'll show you how that works. To give you a flavor of it, what these executions are going to be contain all the memory events of a program, but just one execution thereof. And then find the legal executions from all this set of candidate executions. What's legal? Well, the rules are sort of up to us, right? So this is both good and bad. We can invent axioms. And that's nice freedom. It's not always clear where those axioms come from, but I'll hope to give you an intuition of the most important ones in the next several minutes. Okay. So it turns out, I should say, that most axioms that we care about can be phrased just by using binary relations and an algebra over these relations. I'm carefully not calling it relational algebra to not give you bad ideas about chords, relational algebra, and SQL. Not those. These are relational algebra, as you might, if any of you have looked at them in finite model theory. So you have relations, you compose them together, you take transitive closure, those kinds of relational algebra. Okay. And I'll show you by example how that looks like. So what's a candidate execution then? A candidate execution is just a set of memory events. Memory events meaning reads, writes, stores and loads, and possibly also the fence events that our program produces. But I said the program produces. What I do is I take the program and try to execute it. I'll show you an example very shortly, where we take all the events that come about in a complete execution path through that program. And the loads at this stage anyway, just get some values. That's a candidate execution. So I promised example. Here's an example. Up there is our favorite test. Hopefully it's your favorite by now. Don't answer that question. What we do is we take that program up on the top and find what events, memory events, might that generate. So you see on thread 0, there's a write event that will be generated, and there's also be a read event. And similarly on thread 1, there's a write event and a read event. So we take an execution. Well, also we have to do the initial state writes. And we take one of those guys, we have those events. So we write 0 to x, we write 1 to x, we read 0 from y. So we have those 6 events, yeah, in execution 1. But that's not the only execution. Remember, I said at this stage, we don't look at, or we don't constrain what values we might read. So for example, we might read 1 in y and 1 in x, or we might read 1 in y and 2 in x, or whatever. So there's a whole bunch of candidate executions that we can produce even for very finite programs. And those of you who saw this morning's very nice lecture from Glenn might be getting flashbacks of event structures. These are indeed event structures. So I haven't told you any of the causality relations in there yet. So it's phrased in this way, which is standard in the memory model world. It's a bit simpler than Glenn's event structures because we don't have the notion of conflicts. And for various reasons, historically, we haven't looked at those. But there has been very interesting work by Simon Castellan, who has taken conflict relations. And in that case, you don't have to produce, a million executions or more than a million executions out of one program. Because very naturally, you might say, if I read 0 and x on thread 1, I can't possibly have also read 42. Right. Okay, so that's part of what a candidate execution is. Everybody with me so far? Yes.
What are the red bullets or the black bullets?
Those things are my events. And to the side of them are the labels for said events. Yes, question.
Most axioms can be phrased as binary relation over, I guess,
over events, these memory events.
Actions,
absolutely. Okay. Right. So candidate executions, like I said, have these sets of events, but there's also some relations over them. Now here we might have causality relations, or we might have various different kind of relations. I'll take a particular path through this world of memory models where we have separate relations that we can name and talk about. Let's just draw pictures and talk about particular relations. It's essentially what it is. So what are the relations I'll talk about? So there's really 3 relations, but I'll show you 2 of them because they are very direct from what the program is. The first one is what's called the program order relation. And this is a relation, a binary relation, like all these relations are going to be, between events that are related from where they came from in the program. So if you got an event from one line of the program and the very next line produced another event, you'd have a program order relation between those 2 events. So that's what program order is. And the other relation that I need for myself is what's called a reads from relation, or I'll write that as RF for picture drawing purposes. So reads from relates stores to loads. Okay, so it's a binary relation, which is, you can think of them as typed. The relation starts from a store and goes to a load. And the idea behind this reads from relation is to say that said load got its value from said store, which among other things implies, of course, that this store and this load must have the same value. Show you what that looks like. And that program and the set of event structures that I had. Those event structures come also together with relations. I didn't bother drawing the program order relations, but they are, imagine, sort of going vertically down wherever objects are in a vertical straight line. They came from the programs up above. So on the very left of the screen from your side is an event which is from thread 0. It's a write event of value 1 to x. And there's a program order relation to the next event just below it, which is the read event of a value 0 from at location y. The reads from relation, as I drew them with these red arrows, writes to reads or stores to loads. So in the first execution upon your very left, the loads all get their values from the initial stores. And so you have those two reads from relations. In execution 2, the left-hand thread, the read of y gets its value from the write of y on the other thread. And where does that value 42 comes from? Well, it doesn't, right? There's no 42 written anywhere. Okay, I'll take the question.
Question you already answered in passing, but just to emphasize it. Store is W, load is R.
Yes, I apologize.
Well, no, but if that's a
Writes and reads,
which is
yes.
universal across the literature, it's good to know that there are two symbol systems in action at once.
Yeah.
So people use both writes and reads and stores and loads. And I have tried to be consistent, although obviously not very successfully, in using stores and loads. Sometimes people do make that typing distinction, yes. Okay. I'm really happy with how candidate executions come about. Right. So then we can start looking at these set of candidate executions and finding which of those are legal according to our memory model. And these are phrased by imposing conditions, rules, axioms. In this context, all those three words mean the same thing over the relations that I have here, and maybe others that we might derive out of these. To show you an example, remember Lampert's sequential consistency. Here's a formal definition of sequential consistency, basically by taking Lampert's words and expressing those in more symbolic terms, as it were. So I'll read it out to you and go over them step by step. So suppose we find a candidate execution, some candidate execution from a program, right? We take each of those candidate executions one by one and try to decide whether they are a legal Lamport sequential consistent execution or not. How do we do that? Well, for that, we need, what do we need? A total order, let's call that S, over all the events of E, such that some conditions. But before I get into such that, remember the total order S, that's coming from Lampert's definition of saying, if there is some linear order, right? So if there exists such a total order S. Okay, the conditions then. The conditions say, first of all, that program order of this candidate execution, the program order relation, is contained within this linear order S that whose existence I have postulated. Second, the reads from relation is also a part of this total order S that I have postulated. And the third one, which as you can see, it takes a bit of stating, says that if I have a read from relation between two events, then nothing else in this linear order S sneaks in between. And that nothing else in particular, I mean, the only ones we care about really, are writes to the same location. So let's unpack that a bit. Reads from, remember, is a relation between stores and loads, where that gets its value from that store, which means both of those must operate on exactly the same location in memory and must have the same value. So what we don't want to happen is for some other event, which is a store kind of event at that same location and whatever value to sneak in between. Because the idea is that this linear order S that I am postulating is going to be, as Lamport said, or Lamport was intuiting anyway, this logical time order in which things happen. And if that were to happen, this write or store, excuse me, this store snuck in, then that node would get its value from that store instead of that. And that's the entire content of Lamport's famous definition of sequential consistency, that there exists some sequential order, who knows what that might be, which respects the order specified by the program. Questions at this point? Yes.
Yes. So there was an action that I was expecting to see, and that is not there, which is the fact that every value that is read was written before.
Yes, sorry, yes, indeed. So there should have been that. I should have said there should be, this is a candidate execution where the reads from relation is an appropriate one, which means it gives values to every load action. And furthermore, this is, thanks for mentioning that, that's excellent. Furthermore, since what you had, I didn't write it on the slides, that reads from relation should be, its inverse should be function. So every load must get its value from exactly one store, not more than one. So it gets it, every load gets a value and it gets its value from exactly one store, not more. But I saw the question there. Yes.
That's not cool. Set W in the step R.
That says W is related by this RF relation to R. If there's two events W and R which are related by RF.
So there's a single read.
Yeah. Okay. Yes.
This is sort of, is it accurate to maybe characterize the last part, the if WR in EFR and W prime? Does that capture the intuition that like sort of kind of can't read back in time past? There's sort of
Yes, that's a good way.
does that capture the interleaving?
That's exactly so. So this is kind of the observations were consistent with the sequential order. That's a part of Lamport's definition and report on the slide. Yeah, exactly so. Thank you. Yes. Sorry, say again. The program order. The program order is this relation from the candidate execution that related events as they came from the same thread in program order. So if that write event, maybe go back. The sequence as suggested by the program. Go ahead.
This definition is quite critical in terms of if I were to push through another execution side by side with the shared points in the middle. There's no guarantee that we're going to be consistent.
Indeed not. Okay, that's an excellent point. I don't know if everybody heard, so I'll repeat it for the benefit of the room. Is that this is very much not compositional. If you take one of these which satisfies sequential consistency and you take a different program and then you put them together, there's no guarantee that the combination would be sequential consistent. And yeah, that preempts something I was going to say, but thank you. No, it's good to get this out of the way. Yes, thank you. That's an excellent point. And it's indeed a characteristic of axiomatic memory models. Right. So I told you there were three relations in execution candidate executions, I should say. Wrote it the wrong way around here. And this one didn't turn out to be important to define sequential consistency, at least sequential consistency as Lamport himself formalized it. But it's one that's quite useful in other contexts. And in fact, even for sequential consistency, as you see, sometimes it's convenient. So this is the final piece of the puzzle. The other bit that we get in candidate executions is a linear order of stores per location. So if in your program you are storing multiple times to a location X, then all of those stores are put in a linear order, some linear order, and that order is called coherence. And similarly, if there's stores to other locations Y and Z and W, they're all put in the coherence order, but location wise. So coherence only orders same location stores. Yes.
All stores per application, or is it just of some?
Did I not say all stores?
Sorry,
I should have said all stores. All stores. Thank you. Yes.
What does linear mean in this context?
Linear, just in the sense of order theory. It's a linear order. Total order. Yes. Sorry, I just lost my. Yes. Sorry. My fault entirely. Coherence order, like I was saying. Well, why do we have this in the first place? Well, we have it because all common hardware platforms, they indeed maintain this property that in any execution, all the stores happen to fall out in a linear or total order, and that can be observed on a program. Why do these hardware guys do this? Well, it basically is historical reasons is the real answer. Hardware implementers are, well, in particular for memory level hardware implementers, they're very used to thinking about cache protocols, ways in which permission to store gets transferred from thread to thread. And one of the design principles of cache protocols is that there turns out to be a total order over all stores to unique locations. And because the hardware has it, programmers on said hardware often want to take advantage of that. And because it's there, we do have such a thing. It turns out also to be convenient to define our models, many of them.
Relation. How does that work? So the W there are and W's are right.
W's are right, so stores, yes.
They are right. And right operation reads from I don't know how to
So the way to look about it is this picture here, which not with any intervening means. So stores are always first in this relation, loads are always second. You can think of the relation as typed. And the idea is that load gets its value from that store. Okay.
So when you do your right, with read before,
No, you do the read after getting its value from that, right? Hence the arrow drawn this.
okay.
So maybe a little bit of clarification. There's a history of the notation. In the original level, this was first defined as a function that goes from read to write. That's why it reads from. But it turns out that it's much easier and better to actually have treat the relation this way. So because you were always actually reading about in order that relation in practice. So this is, but the name stays the same because the first way.
Yeah. Thanks, Marco. Yeah, exactly. So red from, yes, exactly. Take care. So maybe I should also say that the intuition of the arrows going this way, as Marco was saying, nowadays we tend to draw it from the store to the load. The intuition behind that is some notion of pausing or time, right? Because if a read read from a write, load read from a store, then the load is sort of sees the value of that store. That store comes before in time, before in causality, all of this kind of. And I would like to have the same kind of picture whenever I draw coherence as well. So if I write 1 and then I write 2, and I want 2 to be the last value for this location, all of these are to the same location. Then I will draw my coherence order CO in that direction. Again, sort of intuiting a notion of time. Right. And that brings me quite neatly into an important derived relation, a relation that I can derive from the data that I had. So the sense in which I mean derived is reads from and coherence, they are given to us by whatever the machine happened to do, right? In this execution, this load really read the value 1. But here's, once we have that data, we can construct new relations by operating over the previous relations, previously said relations. So here's another one, which is, it's almost standard to call it FR or from reads, which of course says nothing at all. But just think of it as reads before. It's called FR though, right? It's a lost battle to change its name to anything else. So what this FR relation is, I just call it FR, is it intuits the idea that this read from before in coherence order, this write. So now the typing of this FR relation is from reads to writes. FR always goes that direction. Okay, and I might have a minute. If there's a RF relation like that, meaning that load read from that store, exactly that store, remember it's functioning in that direction, then anything coherence after is in the FR relation from that load. Okay, yes.
Interesting. CO is the strict overloader.
Yes, that's right.
Strict overloader.
Yes. I mean, alternatively, you would have to take away the identity. Yeah, I've seen it stated both ways. Okay, yes.
Is sequential consistency like your deterministic, so you're going to get the same observed effect no matter what. It's the, I mean, can you have something that branches out and is kind of
No, Lamport wanted you to have a total order, linear order over all the events.
can you have something that is has the same deterministic effect but can reorder as well? I mean, is there
I see what you're asking, and maybe the next slide will answer your question. So
kind of like
if the next slide doesn't make it clear, ask again. Any other questions? Yes.
I don't want to affect the language model, but for the Coherence Order, you described it as like part of it is because of the way hardware designers do it. Does that still apply, or is it still given in language kernel model? So what's the
So it's defined in C and C++, because I said, well, we are going to get it from the hardware anyway. So if I get time, I'll get to the C model where for what's called atomics there, if you have heard of them, there's something equivalent to the coherence order. It's called modification order. That's just names, but you have exactly that same effect, yes. Other languages obviously might take different choices.
But it's not necessary.
Oh, sure. I mean, your compiler doesn't have to maintain any such order. It just turns out that the way C was defined, they said, well, we'll have it anyway. Okay, right. So here's yet another way of defining sequential consistency. So sequential consistency can be defined as so. Suppose we have a candidate execution in the usual way. Then we take the transitive closure of the following relations. We take program order, we take reads from, we take coherence, and we take this FR relation. We take the transitive closure of all that, and if there's a cycle in that relation, then it's not sequentially consistent. If it's acyclic, on the other hand, then it is sequentially consistent. Now, maybe this was getting at what you were talking about, is that some of the choices might be of where coherence is going and where what we are reading from might be forced by the program. But we might have made other choices where indeed there were other choices to be made. Yes. The sort of read from before in coherence order. So it may not be obvious to everybody. It certainly wasn't to me when I saw this the first time, that this is in any way equivalent to Lampert's definition. But it can be proved that indeed it is. So some parts are sort of straightforward to see. Program order, maybe I'll take that question first. Yes.
How did this arise?
Like I said, it wasn't obvious. I don't really know, although it has been known for a while now, since about 1989. It's two famous verificationists, Sasha and Snare, had this sort of characterization.
So they were searching for a market.
Ish. So the real story is what they were doing was they were verifications, right? And at the time, sequential consistency was understood to be the one true way. So they wanted to verify programs under sequential consistency. And it turned out, well, it turns out obviously that to verify something under sequential consistency, you have to existentially find this total linear order. And Sasha and Snare, what they were looking at was, well, that's kind of computationally intensive. If you have n events, finding which of those n factorial linear orders might actually do the trick would be difficult. And they tried to characterize what is it that they needed. And this was, it turns out, the constraints that were needed. Yes. Or union, yes, sir. Union of the relations. So each of those four things are binary relations. You take unions of those relations, put them together in whichever order you please, put them as many of them together as you please. That's a transitive closure. If you get a cycle, then life is difficult. You don't have sequential consistency. If not, then you do. Yes.
So if instead of MR, I just do RF inverse, would I get the kind of equivalent?
RF inverse. I think you would have to post compose it with parts of coherence.
So that's your form.
That's why you need. Yeah, otherwise you'll just get the sort of union, you'll get back to coherence, you won't get anything else.
Which phrase is that? Is that by Lamport?
Sorry, to repeat the
This
question.
is the equivalent definition, but it is by.
The equivalence proof.
Yeah.
The equivalence proof is, as I was saying to Sam, these two verification is called Shasha and Snare. Back in, I think the late 80s it was. What was I going to say next? Maybe I'll answer questions before.
So what's the shaker? Okay, that's the other version. The other way around is straightforward, or is it hard work?
Is it? Oh, the other way is fairly easy. In fact, I can give you the intuition of that bit. That might help. So Lamport's definition gives you a sequential order, right? A total order, a linear order over all events. And if you look at those, look at that total order, you'll see that each of these relations belong in that total. So program order, it's a part of that linear order because of Lamport's condition. RF, likewise, because of Lamport's condition. Coherence, well, okay, it doesn't have to be, but the hardware will give you stores in a certain order, so you can choose your linear order to be in that order. And once you have coherence and RF going, then because you read nothing else snuck in between, then FR is also included. So that direction, hopefully, is easy. So at least it's plausible, I guess. So the other one is, like I said, a bit harder. So PO and RF they are going to be part of the linear order that Lamport wanted. And the other ones, I don't have a sort of snappy explanation for you, but it turns out if this is acyclic, if that combination, that transitive closure is acyclic, then you just take that transitive closure and then find those are the only constraints you need as a clear. So you take any linearizations of the partial order you get by transitive closure, and that linear order then you can show follows Lamport's conditions. Okay. Yes.
I would look this up. What's the name of that?
What's it?
Definition?
What's the name of? Sorry.
Did he just redefine his own definition, or did somebody else define it?
Sorry, I missed context. Who is this he you're referring to?
Well, I'm just trying to there was the original definition, and then there's this new one. So
Yes.
I want to read about it.
Okay. So the first definition I gave you is Lamport's definition. And that you can read about, well, it's a very short paper and it's quite a nice read in 1979. Something like the correctness of multiprocessor programs. This one here is from the late 80s. I'll have to look up the exact reference, but it's by these two people called Shasha and Snare. So afterwards, I could send around via the organizers, or if you give me your email, I'll send you a link to the paper. Yes.
Was there earlier on something saying that our relations have to be inherited? When we define the commutative equation,
Yes.
do we have to that's the RF relation?
So we have to have the RF relation. Yes.
And we can't have right and reads that are not linked by any RF relation. I can say I have right, I have read, and my relation is nothing.
As long as that read gets its value from some other right elsewhere, then that's fine.
No.
No, that's fine. Yeah. Oh, sorry. Let me start again. So every load must get its value from some store. So there has to be an RF relation, but then any other store can be completely unrelated. That's fine. Yeah. Okay. Right. So what's good about this alternative model? except that, you have to scratch your head and see why it works. One of the good things about that alternative model is that it's just phrased as an acyclicity check, right? You took a bunch of relations and you said the combination, transitive closure, whatnot, doesn't have any cycles. Aha, said Dr. Alglove. We can turn that the other way around. We can look at cycles in our relation, and those cycles must correspond to tests that violate our model. And this is the way we get many of our litmus tests, including, for example, our favorite test, the Decker's test. So just to give you a very quick example of that, SC, remember, is that combination transitive closure thereof doesn't have cycles. So what if you had a cycle? Yeah, like a very particular cycle, like there's a program order followed by FR relation followed by another program order followed by another FR. Okay, 4 events with those combinations. Well, if you look at the typings of the FR relation, that forces me to have the first one to be a write, the second one to be a first one to be a store, the second one to be a load, the next one to be a store at the same location, and then the last one to be a load at the location of the very first event. And then program order forces them to be in those threads. Yeah. Are you all right? All right. I take the question.
So I can see how you can enforce read from for the model in litmus tests. How do you enforce coherence? You have to tell the hardware this is happening.
You have to tell the hardware this has to happen. So you have to sort of force 2 stores to occur in exactly that order. And one way of doing that is to, well, this is kind of just a skeleton of the test. You might have to add in other events to force what you want to happen. That's the real answer.
But it's doing automatically. So
It's calculated. It's calculable. And computers are good at doing explorations and doing the calculations. For example, here, like I said, in this cycle, you take that skeleton there, and now you look at, well, the only other thing you have to look at is those FR relations means that load gets its value before that store. Well, it has to get its value from somewhere, right? Somewhere before that store. So we need an initial value that would give its value to said load. And that initial value now better be coherence before this store that we just have. That's what FR means. In other words, if you fill in all the blanks, you get back an execution corresponding to the Decker's example I have shown you many times already, where you write some value to 2 different locations, and then in program order later, you load values before the something that you had just written. And this kind of filling in the blanks, going from cycle there to real concrete values that we store and initializations that we do and things like this. There's effective algorithms for this kind of thing. And this is how we find tests. In fact, lots of different tests. Okay, yes. Coherence order says that there's, for every location like X in this program, there's a linear order or total order on all stores to that location. So we look at a candidate execution. Where are there stores of X? There's the first one in initialization and then one here on that thread. And there has to be a linear order for every location on stores to that location. So there has to be some order between. And similarly, there has to be a coherence order on other locations in the test, like Y. That's all coherence order is. And like I was saying, this comes from the hardware doing stuff for us. The hardware really does do this. 0 was a value in location X first, and then it changed to 1. And that's something that can be observed. Okay. It's sort of causality. It's certainly a notion of time.
Yeah.
From the point of view of location X, 0 happened before 1. If that helps. Okay. I think I have spent about 45 minutes on this. So very quickly, what I'll do is I'll finish up just this bit and then take a short break. So as was anticipated already, axiomatic and operational models have different strengths. So axiomatic models, they are easier to state. The SC operational model wasn't that difficult to state, but needed a few rules. SC in axiomatic style, it literally fit on one line in my slide. 4 relations, transitive, closure, and union, that's it. And correspondingly, the checking whether some behavior is allowed or not is typically much easier on axioms. You just have to check a bunch of conditions over your relations. Operational models, they are not so great on these 2 aspects, but they have their strengths in other ways. So first of all, I personally, this may not hold for anybody else in the world, but I think it holds for at least some other people. I find them much more intuitive. It's much easier to find what's going on if you can think of an abstract machine model. Maybe that's just because I think in abstract machine or operational or syntactic terms. But that also has benefits in being able to do incremental calculation. You know, my abstract machines do some stuff, and then I can stop and inspect the state, and then it does some more stuff, and then I can stop and inspect the state again, and so on. Axiomatic models, not quite like that. You have to take the entire candidate execution and then check whether it's legal or not. So in other words, you have to basically execute your program completely. Well, okay, up to coming up with possible values that you might have read in all your loads. And then you have to check them one by one. So it's not a very modular form, or at least not very straightforwardly modular. In other words, if you have, as Ohad was saying, a legal execution and another legal execution, if they are stated in axiomatic ways, then it doesn't very naturally compose. For example, if you want to think of the properties of your library function and then the caller of that library, that's a bit hard to do. Operational models, that's where they shine. You can take the state of the entry to the library function, do some incremental calculation, find out the post condition, this kind of thing. Yes.
How do you claim this event structures fitting there?
Very good question. So I don't have a full answer. So these, at least I was being very, very syntactic. And in particular, what I was doing was, like I said in the beginning, having a set of events, what Glenn might call event structures, or the very, very simple event structures, a whole set of event structures per program. Whereas what you really want to do, of course, is have a small number, one event structure as the meaning of a program. And for some memory models, Simon Castellan has included conflict relations and things like this to make that happen. You notice I didn't have any conflict relations. I did have some things that looked like causality, or at least they had a direction.
Yeah, I mean, I guess the more concrete way of stating the question is how would one connect specifically the axiomatic models to event structures, or the operational models to event structures, or do you not know?
I don't have a very good feeling of how you would go doing it. I've seen it done, like I said, Simon's work, but I'm very much not an expert. Okay, so if there's good properties of both, naturally you want both styles, right? And you want them to be equivalent. I'll not take any time. I'll just say that we can do this for the SC models that we have seen. All operationally allowed behaviors we can prove by looking at how the operational model came up with those, with justifying those behaviors, show that they can be also allowed in the SC axiomatic model. And vice versa. For SC at least, we have an equivalence proof. You can go in both directions. You take an axiomatically allowed execution, and with a bit of head scratching and a bit of work, you can work out a justification in operational world. And that's a kind of good property you want of your models. Yes.
This one you understand the model?
It does do some. Obviously, we want this for all our models, right?
No, semantically.
Could be, but you'd hope to get a precise approximation if you can, of course. So I promised you a break, and I'll break on this slide. For axiomatic x86 TSO, we can write an axiomatic model. I won't tell you what it is. I'll just promise you it's fairly simple. It's not one line, but it's actually not that many lines. It's about 4 lines, I think. Yes, 4 lines, because I wrote 4 bullets here on the slide. I won't bother telling you, because of time, I won't go through these points in any detail at all. I'll just say it can be done. And for that, we have an equivalence proof as well. I do have a pointer on the slide to where you can look at. So you don't have to believe me that it's, simple. It is actually quite short and simple. And I'll take maybe a 5-minute break. That's appropriate at this point. Pause. Yep. Okay. Let's carry on. Right. So I am aware I only have about 45 minutes to tell you the glories and wonders of many other memory models. So I'll make these slides available. I don't know if I'll get through all of them, but hopefully we'll have some fun. In the time that I have, let's talk about even weaker memory models, as Philip was asking for. So the background here is that sequential consistency is really strong. x86 TSO, while weaker than sequential consistency, it's really quite strong as well. But there's other architectures in the world, and some of them have much more interesting memory models. For example, IBM Power. This is the architecture that's on big cloud servers. Or ARM, everybody's heard of ARM. If you haven't, they power almost guaranteed your cell phone. The most recent MacBooks, they come with ARM processors. And I have a typo there, it should be RISC-V. RISC-V is this new architecture which is being developed in an open source form. It's quite exciting because you can really peer into the innards of what an architecture looks like. It's all open source, and you can look at all the different things you'd want to do with architectures. So all three of these have much weaker memory models than x86. And let's show you ways in which they differ. To show you this, I'll have yet another litmus test. This one we call message passing, or abbreviated MP. So just like before, just like the test you have seen before, there's two locations in play. I'll call them D and F. There's two threads in play. So this time, thread 0 over there on the left, it does two stores. First, it writes to D, and then it writes to F. And on the right-hand thread, thread 1, it waits around, waiting for F to become non-zero. Remember, F was initialized to be 0. After that, in the program order, we read from that location D. And the reason this is called message passing is this is meant to encapsulate a very common idiom of thread 0 being a kind of writing thread. It's D being data, it's mangling about with a big data structure. Here it's just one location. In principle, it could be a big data structure in memory. It's doing stuff to it. And finally, but only after it's done, it sets a flag saying, now this data structure is available for other people to look at. And then the reading thread, it only does reads there. It loads from F first, that's the flag variable, hence the name. And only when it sees that it has been flagged, that the data is ready to be consumed, it goes and looks at data. And you would hope that if the reading thread has exited the loop, in other words, it has seen the flag being set, then it sees the changes made to the data structure. It doesn't anymore read the old value in D. And if you are thinking in sequential consistency world, this is clearly true, because the while loop can only exit when it sees that flag being set, which means all of thread 0 must happen before all of thread 1. And even on x86 TSO, because the store buffers are first in, first out, before the store of 1 to F makes its way to thread 1's load, the store of 1 to D must also make its way there. So it would be forbidden on x86 TSO, and we can test this. It's never observed on x86. On some other processors, meanwhile, it's very much observed. How come? Well, there's many different possibilities that might have happened. So I maybe hinted at one already. Store buffers may not be FIFO, right? Just because thread 0 did those two stores in that order may not force the hardware to make those stores make its way slowly along to the other thread in exactly that order. For whatever reason, we might quickly grab ownership of the F line before we grab ownership of the D line or whatever. So the stores may not be making their way across in order. But also, of course, just because I wrote the program in that way, doesn't mean the hardware has to do those instructions in that order. So in x86, I told you the thread subsystem was quite boring because it did everything in order. But hardware folk, they love speculating things. It's now time to do something, and as long as nothing stops me from doing it, I'll do it. So I don't know the resources for writing 1 to F might have become available before the resources for writing 1 to D. So let's do that first. Nothing stopping the hardware, because as far as the hardware goes, those two locations are different locations. Nothing much would go wrong if we did them in other orders. And likewise, on the reading thread, there's two loads in play, the load within the while loop and the load after. But just because I wrote them in program order that way, the hardware doesn't think it needs to do them in that way. Maybe it does branch speculation. It speculates that the while loop is going to be executed very soon. So let's go do that next load. So all those are possible mechanisms, any one of which would show us the questionable value for message passing, the non-sequentially consistent behavior. It turns out the later two architectures there, they do all three of them. Any one of them would have been sufficient, they do all three. Just because you write programs in a certain order, they don't plan to keep your stores in that order. Neither do they plan to keep your loads in that order. And finally, even if somehow they happen to happen in order, by the time it starts making its way into the wide world, into being looked at on other threads, the interconnects might reorder them all. So yes.
So if it was not different variables but the same, would also, I mean.
Excellent question. If they were all the same, then because these hardware guys have taken as a religion coherence, they would say to themselves, I don't think I want to do that. So current day hardware, they all maintain coherence and they wouldn't do it if they were to the same location. So they pay attention to which location you're storing at or reading from or whatever.
So if the reads are not in order, then will the second read first?
If the reads are in order, sorry, I think I'm missing context. If the reads are in order but in different locations, or
I thought that you said that all three happen, so that reads could happen out of order there, but they reads to the same location will happen in order. Is that it?
Yes. So both stores to the location and loads from a location will happen in order. Because otherwise, you see, you could observe coherence violations, and hardware folk don't like that. Okay. Right. Yeah, question?
What is the difference between the two first and bullet points?
What's the difference between the two bullet points? So the first one is getting at the thread itself, maybe doing the stores out of order. So just because I wrote the programs in that order. But even if the thread, the core was doing those in order, after it has done that, remember there's buffering and caching and all this in the system. So if it makes its way to other threads, are they still going in that order? That's not guaranteed. So the second bullet point is saying that they observably violate. In fact, they don't very much care about the first in, first out nature of x86. Right. Another test for you. Remember Decker's example or store buffering example. That's the reason behind the name SB for that test. So we were buffering stores. Why can't you buffer loads? Possibly you can, right? So here's a test designed to find out if loads are being buffered in the system or not. So here we do the loads first, and then we do the stores. And I've got the condition the wrong way around. Sorry, the condition should ask, can both of them see the later stores? There should be all ones. So if that were to happen, then the loads are somehow getting buffered, delayed while the stores are happening later. So that's a very confusing typo there. It should all be ones. So the final condition is R0 is 1 and R1 is 1. And that couldn't happen because sort of for inverse reasons, at least one of those loads would have to happen first in Lamport SC, which means it couldn't take its value to be 1. And similarly, it would happen on TSO. Now here's an interesting bit. All the architectures allow this, and they allow this for the reason that the hardware folk, we talk to them, are very insistent that one day they might come up with load buffering. They see no reason to tie their hands behind their backs and not do load buffering. But it's an observable fact as of today in 2022 that no commonly available hardware seems to be doing load buffering. But they really want this to be allowed, so our model has to account for the fact, for the possibility, excuse me, that it might be allowed. Yes.
So when you say current hardware doesn't show this, that's just your evidence for this is attempting to exhibit this on current hardware and not
Exactly so.
It's possible it doesn't work. It's just it's so rare that you never see it.
Yes, indeed, that might happen. I mean, this is the usual testing, can only show the presence of bugs kind of idea. Yes.
So we are talking sometimes to the architects. So we won't be able to do it someday. They will confirm, but we're not currently doing it.
That's right.
Okay,
Yes.
so it's a bit stronger than that.
It probably isn't.
Unless they provide someone.
Yeah.
Still then, all about
That's, yeah, exactly so.
Do you know why they want this to ever?
Because they can imagine for themselves load buffers where they stop loads from happening because it turns out to be more efficient that way.
So for the issue of trying to know that you don't do it yet, then
That's it. Yes. So they know how to do it. They just haven't done it yet. Okay. So what happens if you do need to reimpose order? You remember in x86 land, we had a fence or a barrier called mfence. And all these architectures, Power, RISC-V, all of these, they do have fences like that as well. The idea being you stop any reorderings that's going on. They're called different things on the different architectures, but they all have them. But because they permit themselves many more kinds of reorderings than before, they allow reordering to stores which happen to be in program order. They let you selectively barrier or fence kinds of events. So for example, on Power, you get a kind of barrier. If anybody does Power assembly, it's called LW sync, lightweight sync, which does not order a store before it and a load after it, but does every other combination of stores and loads. There's a similar one. In fact, there's many similar ones on ARM, what they call dmb.st for store and dmb.ld for load. Stops reorderings of some kinds of events. For example, for dmb.ld, only loads before and loads after, and loads before and stores after, but not other kinds like stores before and loads after, things like that. And differently on dmb.st. And RISC-V, I think this is the most modern of the architectures. This is the one that, like I said, they're developing in an open source manner. They said to themselves, well, we see this pattern now. Let's just get all of those combinations in our architecture. Anyway, the point behind this is if you are programming at the assembly level on one of these architectures, You could just have a full fence like you used to, or you could be more selective. And the reason you want to be more selective, of course, is that they might have different costs. I haven't talked at all about how performant these things are or not, but you might imagine the weaker fences are more efficient to implement than the stronger ones. Okay. Right. How much time do I have? Okay, time enough for me to tell you a bit more about this before I get to C11, which is also something I think people want to hear about. So, yeah, let's talk about dependencies, right? So, in message passing, in the MP test, if the stores are somehow stopped from being reordered with respect to each other, like for example, if you had a store-to-store fence and we stuck that in, I said before that the architecture is allowed to, and the hardware is allowed to, and in fact, very much does reorderings of loads as well. Even though, you know, one of the loads was after exiting a while loop that was guarding the first load. But the programmer possibly was thinking about that first load of flag to be in some sense guarding that next load, right? At least that was the intention, right? Going round and down in a tight loop, waiting for that flag to be set. So that's what's a kind of dependency. And some of those dependencies, the hardware pays attention to and does not feel free to reorder things as it might have done. So Anders pointed out one of these kinds of things. If they are to the same location, the hardware doesn't feel it's legitimate to reorder. But there's also sort of these kinds of dependencies, and there's many kinds of them. I'll give you a quick summary of the kinds of dependencies people have considered. But really, these dependencies are things programmers use and expect to work. Sometimes they really do expect it to work. So for example, the parts of the Linux kernel, what's called RCU. If you have heard of it, you have otherwise. It's just a very fancy concurrency unit within Linux. Anyway, it depends the way it's coded very critically on some dependencies being observed by the hardware, being paid attention to by the hardware. So what kinds of dependencies do we need? So here's a kind of dependency. It's called address dependency. So suppose you load a value, right? And you use that value to calculate the address of some other memory access that you're going to do next. For example, you load the value of the beginning of an array, and then you do some calculation to index into that array, and then you do some operation on that part of the array. That's what we call an address dependency. Similarly, you could think of data dependency, where it's not the address that's changing depending on the value you just read. It's the data that you're going to, well, you have to store it because you can't load a bit of data. It's the data that is dependent. So that's what we call a data dependency. Another one is what we might call control dependency, where this one you saw already, it was in the message passing example. You read a value, and this was used to calculate whether you should or shouldn't do subsequent events. So things like if you load a value, then you do an if-then branch, or maybe a while loop, depending on the value you just read, that kind of thing. And in the interest of time, I'll skip over another kind of dependency that is in there. Whoa, what's happening? Right. yeah, what I wanted to get to is that some of these are written by the programmers naturally in the algorithm. For example, when you are doing this kind of message passing, you are waiting for a flag to be set. That kind of thing is naturally in the algorithm. But the hardware doesn't know what is natural for your algorithm or isn't. So it just looks at all dependencies. And in fact, hardware also respects so-called fake dependencies, which means the hardware is not very clever at doing optimizations over your dependencies. What do I mean by that? I mean, for example, if you read a value and XOR it to itself, that's a favorite example of the hardware fork. Then, oh, that's 0. And if you then try to store that value somewhere else, in principle, you know, the value, only the value 0 is ever going to be used ever after. But the hardware will still think that's a dependency. Back in the old days, this was because, of course, the hardware didn't have enough resources to quickly calculate whether it would be always 0 or not. And because programmers have started depending on this kind of dependencies, they guarantee forevermore that they're not going to optimize away that bit. Okay, like I said, I'll quickly skip over things. Some of these things, most of these dependencies are paid attention to by the hardware in the sense that they stop themselves reordering. That's all I'm going to say on that. I'll show you instead by example forbidding dependencies. So this is to show off my assembly programming credentials. I'll write, stir and low sync and stir and lit. It's just assembly. It's hopefully, even if you have never seen power assembly before, hopefully this should be fairly self-explanatory. It's exactly the message passing example from before. You do a store of 1 to D, you do a store of 1 to F, and on the other thread, you do in a loop, read that value until value changes, and then you do a load. In between, I have stuck in some of these weaker barriers. That is, in this case, enough to stop all of the mechanisms for message passing, the questionable behavior being observed or not. And in this case, we would, yes.
But look, any of the threshold ones, you see the weak behavior.
Yes.
So, so you need to know what you're doing, like.
You need to, yeah, absolutely. Okay, maybe I'll spend a bit more time on it actually. So I said before that there's 3 mechanisms that led to the questionable behavior coming up. And you need to make the hardware aware that all 3 of those should be taken away. So what are those 3 things? Well, the 2 stores, we have to stop them from being reordered. We need a store barrier for that. That's what that one is. That barrier, I didn't tell you this, but it's true, also makes those stores propagate in exactly that order. So that gives us that one. So finally, we need to keep those 2 loads up to occur in exactly that order. And there's many ways you can do that. One of them is what's called a control async dependency. And I'll stop there. Yes. Okay, anybody else? No, okay. Okay.
What's the different performance? So if you bind this text,
so it has a cost, for sure. It doesn't have as much of a cost as the full barriers, which is sort of a nice thing to do. Anytime you want to stop reordering, you throw in a full. So these are okay. Yeah. So the point of showing you all these fun examples is to say that all of these architectures, they have very, very interesting thread subsystems. In sequential consistency and x86, the thread subsystem was boring. All action was happening in the storage subsystem. Here, much, if not all of the action happens in the thread subsystem. Because the thread subsystem takes your program as written, but it doesn't do them in that order. It reorders whatever you got in the program almost arbitrarily. The almost is important because obviously there's cases, barriers, dependencies, what have you, where it does not do these reorderings. Any questions? Okay. Taking James's advice of killing your darlings, in the interest of time, I'll skip over one of my favorite pets of the power model and move to programming language models. I'll make these slides all right because you really should look at it after. Anyway, programming language models. You might say to me, well, I know you like programming in assembly, but just because you do, I program in high-level languages. So the question is, are you safe from all these weak memory models things if you were to program in high-level languages? For current purposes, C counts as a high-level language. Okay, well, the answer is clearly no, right? Because C has to be compiled down. In fact, every language you write in has to be compiled down to run on exactly the same weak memory hardware that we are talking about. But let's leave aside that problem for a bit. Let's imagine that the world is great. We have sequentially consistent hardware in our back pockets. What then? Well, even then, you are in trouble. The reason you are in trouble is that your compilers are conspiring against you. They are optimizing stuff. Just as well as the hardware is optimizing stuff, the compilers are optimizing stuff as well. And in most situations, that's a good thing, right? We do want them to do optimizations. We do want our programs to go fast. But sometimes it has maybe unintended consequences. Let's see message passing once more to sort of subtly hint to you that we are now in programming language world. I'll use bigger variables like data and flag. It's exactly the same program as before. I'm just kidding. Well, it's exactly the same, except on thread 1, I preload data for whatever reason the program is written. And I'll write this program in this way, but you should imagine to yourself that there might be lots of other stuff that's not important, not relevant, in between each of these lines that I have written. Okay, can we see R equal to 0? It's the same question as before. So yeah, I really haven't changed the program. Okay, your compiler now takes this program and has a go at compiling it, right? And what a compiler might say is that, look there, I have 2 loads from data. On that thread, nothing else is writing to data. So as far as local things go, that doesn't look like it's changing. And maybe on the hardware I'm compiling 2 loads is a bit expensive, right? Registers much easier. That's actually true, universally true, no matter what hardware you're running on. So many compilers will take a look at that program and say, aha, common sub-expression, let's eliminate that. Let's do a cheap look at register kind of thing instead of doing an expensive look at memory kind of thing. And now, once it has transformed your program in this way, even if you had sequentially consistent hardware, of course, the first load might happen before the flag got set. And you get the non-sequentially consistent behavior, even though you had sequentially consistent hardware. That's unfortunate. Should you even be writing programs like that? So these people, Saitadvi and Markel, will tell you that you're a bad person for writing programs like that, because it looks like you're writing racy programs. Programmers should not really be writing races. That's not a good thing to do. And this idea is kind of at the basis of C11 concurrency, which I hope to present to you in the short time I have left in this lecture. So these models are what's called data race free. That's quite a mouthful. What's that really mean? So what that means is that if you don't write races, if you're a good person, then your programs have sequentially consistent behavior. We are back in Lampert's ideal world. Life is good. This is just a programming model. Yeah, how this is implemented, we'll come to that bit later. But as a programming model, that's quite nice. If you don't write races, you get sequential consistency. If you write races, you're a bad person. You'll get a rap on the knuckles. In fact, you'll get more than a rap on the knuckles in current C and C++. You'll get undefined behavior. Your programs can do whatever in the usual sort of C and C++ way of saying things are bad, things are undefined. Okay, so easy then. Let's not write any races. How do we avoid those races? Well, we could always do shared memory accesses properly guarded by locks or mutexes, as you might call them in C and C++. And that will be sufficient if you always lock your accesses. That will be sufficient to give you sequentially consistent behavior. C guarantees this. It's a compiler's job to implement that. It's possible to do it, at least, but not too much expense. And that's kind of a good model, a good programmer-friendly model. Hence, Advi and Hill have been pushing this for quite a while now. Of course, when you translate this to the low-level programmers, you tell them all that. They say, well, some of us implement mutexes. What are we supposed to do? So that's problem one. Second problem is that, well, you as a programmer properly locked your shared memory accesses. But then, like I was saying, the compiler gets in the way, right? It optimizes things, it moves your accesses around. Maybe it took an access that belonged inside the locked region, outside the locked region. Oops. So we have to have ways of telling the compiler, please compiler, don't do that. So the option 2, which is what current C and C++ is steering us towards, is to make a distinction between the normal accesses that you and I write. They call those data accesses, and other shared memory accesses that are specifically intended for use to write synchronization. So you call them synchronization accesses, or to use the correct terminology in C and C++ terms, what they call atomic accesses. These are syntactically marked in the program. So the compiler can indeed look at them, pay attention, and do sort of special stuff that it wouldn't do for your normal accesses. So if you haven't seen these before, you haven't programmed concurrency since 2011 or thereabouts, then this is how they're written. But you don't really need to know, they are just syntactically marked. Of course, if you have programmed concurrency, you've probably seen these a million times already. Yes.
So students to that volatile, which in this specific case might actually solve the problem. How does it relate to atomic? So it might not even solve the problem.
Ask me later.
Okay.
It's different from atomic. So volatile was something that old C programmers used to write. And when they created this new mechanism, when they really thought carefully about data accesses, they realized that it didn't solve all the problems. So they're just different things. No, there's use cases for volatile, but not for this kind of thing. And the other differences, yeah, come back after and I'll tell you more than you ever want to know, really. Yes. You can have CSS, classes, and things like that. Yes, absolutely. Okay, other questions? Right. Okay. So that's all you need to know if you are, Joe average programmer who only uses library functions to do all their synchronizations and everything else. And everything else we properly lock. That's all you need to know. But of course, C programmers, if you're programming in quasi high-level languages like C, you probably really want to do stuff, low-level stuff, right? System C stuff. So for those algorithms, C11 gives you several different options. So first of all, like I said, it specifically marks synchronization accesses or atomic operations. And not only can you mark them, you can mark them with parameters. And these parameters, really, you should think of them as how strong do I want to be? So there's several different ones of them. The strongest one is what is the default. Like I said, the things that they expect Joe average programmer to be using. So these are called, more technically, the sequentially consistent atomics. There's other ones as well. The weakest synchronization or atomic kind of access is what's called relaxed. Just relax all consistency. And there's intermediate ones, some of which are dead handy, release and acquire. Show you an example of them. And some of them, it's not really clear what they mean. You laugh. So they had an idea of what they might mean, and then it turned out didn't really quite fit in with the rest of the model. So in the very latest version, in C20, they say, temporarily, let's not use these guys. We get back to you when we know how to specify these properly. But people do want to use them. So I think, yeah, that's ongoing work, basically. Right, how does C11 think about its memory model? So it thinks about it in an axiomatic model kind of way. Axiomatic models, as we just saw, memory operations, events corresponding to said memory operations, and binary relations over them. So C11 has a key relation that they call happens before, or Z causality, although they don't want to call it causality. And this is, like all our axiomatic model relations, a binary relation between memory events. And it really is meant to have give you an intuition of what things must happen in time order. That's the intention, anyway, of the happens before relation. So one way to, sorry, not the one way, the only way to write good C programs is to write data race C programs. And for C purposes, what's a data race? Data race is standard accesses, non-marked accesses that are not related by happens before. Which of course brings up the question of, well, how do you establish happens before? I'll say that the weakest, before I go to that question, I'll say that the weakest kind of marked accesses or atomic accesses, the ones that are marked with the strength of relaxed, They don't create any happens before, but they don't create data races which would create undefined behavior either. Okay. Right. Happens before. How do you make yourself some happens before? Remember what Advi and Hill wanted you to do. They wanted you to let's say this and then answer a question. They wanted you to guard all your non-atomic accesses by locks. So in C11, then your locks and unlocks create happens before. But there's other ways as well, which I'll get to shortly. But I'll take Ohad's question first.
It only happened because of the behavior of the population or another several data.
No, data races are defined exactly in terms of happens before. Yes. But happens before is a more complex relation that you might imagine. Yes. Absolutely. Yes. It's a compiler's job to check all of that. Okay. How much time? Ish.
Probably be wrapping up.
I should probably be wrapping up. Oh no, then I can't tell you about happens before, which is sad. But let's not tell you about happens before. I just say that you can write your message passing examples with atomics in pseudocode, basically there. And you give them all relaxed annotations. If you say they are very weak, no happens before gets created, and you start seeing non-SC behavior. And that's good because then your compiler can do all the optimizations it really wants to do to your program. And the hardware can do all the stuff it does. And you see the non-SC behavior. But if you really care about making message passing programs work, then you have to instruct the compiler not to do those optimizations and instruct the compiler to tell the hardware not to do those reorderings or whatever. In other words, to insert appropriate fences, barriers, what have you. And you can do that. Right. So I had in mind to tell you what you can do next. What you can do next, I'll say 2 words, 4 words, maybe. You can do model checking. Model checking is great. It's a really well-proven technology, as was mentioned earlier in the week on programs. But model checking so far for concurrent programs has been worked with under sequential consistency. Under weak memory, it's a work in progress because the key problem is that sequential consistency, it's a nice model. You have interleavings. And your model checking can look at all those interleavings, explore all those interleavings. In weak memory models, it's not just interleavings. It could be just interleavings if we created these operational models with more stuff. But then there's more stuff, right? The state space basically becomes much bigger. So the ongoing work is how do we reduce that state space? And the other 2 words, sorry, is to mention the word program logics at you. Program logics, these are ways of verifying your programs by hostile assertions. And for anybody who has not seen program logics before, I'm not going to make much sense. But for those who have seen them before, again, the standard way of doing program logics for concurrent programs has been assuming sequential consistency. And that's not sound for weak memory. So what you can prove under these program logics under sequential consistency for programs does not mean those programs have the same properties when you execute them on modern hardware or indeed under modern compilers. So much exciting research to be done. Please join me. Thank you.
Thank you very much, Susmit. And we have a quick tea and coffee break, as far as I understand. And we should meet back here at for Samsung.